Okay, so last time we started our journey into the discussion of now magnetostatics. So we now are including not just the forces due to electric fields, but the forces due to magnetic fields. In general, of course, our electric and magnetic fields can be time dependent, but at the moment we're dealing with the static case. And more generally, if I have a distribution, these are the forces. Remember, these are not the self fields. These are external fields. Okay? The self field of charges on themselves is a very delicate question. So, in thinking about magnetic phenomena, we think about the sources and also the objects upon which there are forces are the currents. And we express that in three-dimensional space in terms of the current density. And the current density can be thought of as the local flow of charge density. Okay? And the current density, even though it's a current moving in three-dimensional space, has units of current per unit area because of this flow. It's always a confusing thing. So the current that flows through a surface is the flux of the current density through that surface. We can also talk about current flowing not in three-dimensional space, but combined itself to a surface, in which case we talk about the surface current density as the flow of surface charge. That is charge per unit area times velocity. And the units of the surface current density is current per unit length. Okay? So we're right now concentrating on magnetostatics, which is the situation in which we have a so-called steady current, which is expressible thinking about the so-called continuity equation, which is, in this case, the equation for the conservation of charge. And what the continuity equation tells us is that charge is neither destroyed or created, but only flows from one place to another. And that is expressed as a global statement. Says that if I have some volume and there's stuff going around in it, whatever this volume is, the rate of change of charge inside that volume is decreasing only if current is flowing out from the surface. Okay? If it's flowing in, then it's negative, and that negative sign makes this increase. And that's expressible locally, saying that the local charge density changes only due to a convergence or divergence of the current density. And in magnetostatics, what this is saying is that the divergence of the current density is thus zero. So that is to say, the local charge density neither builds up nor spreads out if this is zero. So magnetostatics and electrostatics can be treated in the same context, because electrostatics means that the charge density is constant in time. That's electrostatics. Okay, so the currents themselves are the sources of the magnetic field, and we express that to start after the empirical law, the Biot-Savart law. Which tells us how, if we have some current density, J, how to find the magnetic field that is generated by this source in terms of an integral over the current density. Okay? And we kind of went in reverse order here and said the Biot-Savart law tells us something about, we could derive the field equations. It's really backwards. I mean, the field equations are the fundamental thing. The field equations here are del dot P is 0, which tells us that the magnetic field itself is the curl of another vector field. You remember from our first problem set, any vector field is determined by its divergence and its curl. Since the divergence is 0, it must be the case that the magnetic field is the curl of some other field. There's no piece that's the gradient of a scalar, because that's related to the divergence of B, which is 0. Go back and look at Helmholtz theorem again. The curl of B is not 0. It's given by 4 pi times J over C. And that is Ampere's law. Okay? So these are the fundamental equations of magnetostatics. We'll go backwards in a moment the right way and show that the Biot-Savart law is the solution to these equations. If I thought about these as the empirical laws, then this is the solution to these field equations. Okay? So once I have these equations, which are the parts of Maxwell's equations associated with magnetostatics, in principle, we can solve any magnetostatic problem. So, as in electrostatics, when we have situations that are of high symmetry, we were able to just use Gauss's law to very quickly determine what the electric field is. Analogously, if we have the high symmetry, you know from freshman EM that you can determine the magnetic field instantaneously using the integral form of Ampere's law. So if I integrate this equation as a flux through a surface and use Stokes's theorem to relate the flux of the curl to the circulation integral, then we have the integral form of Ampere's law. Okay? So the integral form says that the circulation integral of the magnetic field around a closed contour is related to the flux of the current density through the surface enclosed by this with the right-hand rule relating the circulation integral to the direction of the flux. Okay? And while this is always a true statement, it's not always so useful as the method for determining B, just like in thinking about Gauss's law. But if you can, man, that's the easiest thing in the world to do. Okay? In the same way, if you tried to, you had a sphere of charge and you wanted to find the electric field, if you tried to integrate Coulomb's law over that sphere, it's a pain in the something. But, you know, doing it with Gauss's law, you know, just blink your eyes and you're done. Similarly for Ampere's law. And when is that? So let me just very, very quickly remind you, this is something that is, I'm sure, quite familiar to you from your undergraduate studies. The point is, if the symmetry allows us to a priori know the form of B such that for a well-chosen contour, this is just equal to the magnitude of B on the contour times whatever particular length of the contour along which that is non-zero. If we could just write that out, if we know that's true, that's not always true, right? I mean, generally B, we don't know the form, we don't know what contour to choose. But if it's such that base of its integral is trivial, and you can just write B dot dl as the magnitude of B times the length of the contour, you've solved it. Because then that's equal to 4 pi over C times the enclosed current, also known as mu naught. And we could just solve then for the magnitude of B. And we know the form of B, meaning we know its magnitude and its direction. All right? So the most trivial example of this, which is the analogy of the point charge, but for magnetostatics, is the current, line of infinite current, right? If I have a line of current, infinite line, then we know from symmetry that the magnetic field must be azimuthally symmetric, because this is azimuthally symmetric, and it points in the azimuthal direction. So if I stop trying to draw perspective because I'm so damn bad at it, here's the current coming out of the board. Then we know the magnetic field has to be of the form, if this is the distance r from the radial distance r perpendicular to this, and the magnetic field is only a function of r and points in the phi hat direction if this is the z direction. So the hardest part of Ampere's law is that. Then you're essentially done, because the circulation integral then, well, we should choose the curve with circulation to be the circle of radius r, in which case the integral b dot dl, so b is along the direction now it's really not quite true, because of course it depends on phi in the sense that this depends on phi, right? Let me just leave that in there. This is a tricky point. I mean, phi itself, phi hat, is a vector that depends on position, right? Phi hat is this vector over here, it's that vector over here, it's that vector over here. Curvilinear coordinates are such that the unit vectors depend on where you are. Cartesian coordinates are special in that x, y, and z are the same vectors. The x hat, y hat, z hat vectors are the same no matter where I am. Okay? But these are functions of position. So, but the point is that this is thus equal to, since dl is equal to the radius d phi in the phi hat direction. This is equal to v of r times 2 pi r. R is a constant, can come out, the integral d phi. Well, that's the formula. If you just look at it, it's the perimeter times that. Okay, and that's equal to 4 pi over c times the current enclosed, which is I in this case, because it's coming out. And so what we find is that the magnetic field associated with a wire, an infinitely long wire, or something which is approximated that way, v of r is equal to 2 pi over c times I, 1 over r in the phi hat direction. So the magnetic field falls off like 1 over r. Now this, of course, is an infinitely long wire. There's no such thing. It's kind of a false problem, but it's, as I said, it'll be approximately that. Sorry, there's no pi here. Yeah, okay. That's the most trivial example. Another quite trivial example, just to quickly remind you, is a solenoid. I have a solenoid is a situation where I have surface current around the cylinder, which I can think about as, you know, and there's all these little circular loops of wire going around this cylinder. Okay? That's my solenoid with current flowing in each loop I. And this is supposed to be very densely packed. There's no space between these wires. It's meant to be uniform surface current. And there's n turns per unit length, right? So that is around this. I can also think of it as K is the surface current density flowing azimuthally around the cylinder. Okay. So, in this case, it's not as trivial as this is what is the form of the magnetic field of the solenoid. You have to do a little more work. But first of all, we know if this is infinitely long, the magnetic field can't depend on where I am relative, when I'm outside this thing. It can't depend where I am relative to the center of the solenoid, because how far away am I? There's nothing to tell me. It's infinitely long. It always looks the same. And since it falls off in some way, the only solution that must be is that B is 0 outside the solenoid. That's the only possible solution consistent with the magnetic field falling off some way and being constant. It's got to be 0 everywhere outside. Inside, it's not as trivial, but you can prove with the Biot-Savart law that B is constant inside. That follows from a little bit of work, not so trivial. The direction of the magnetic field, though, we do know from the right-hand rule, has to be along the z direction. It's going to be constant. It's the only direction it can be in. So what we have is that the magnetic field, putting this together, what we see is that the magnetic field is 0 outside and some constant in the z hat direction inside. That's the hard part. Now we can trivially solve for the magnetic field based on the appropriate choice of the Amperian loop, analogous to the Gaussian surface. What loop should we choose? Well, we should choose the loop such that B dot dl is constant along that loop. So if I, again, draw this no longer in perspective, but in cross-section. So here are those terms with current coming out of the board over here, and that's current going back into the board over here. Then I should draw my Amperian loop like that, because the integral V dot dl is what? Well, if I call this length of this thing L, B is constant along here. V dot dl, the only leg of this loop which contributes to the circulation integral is this. Because B dot dl is 0 here, because B is along the z direction and this is perpendicular to it. So B dot dl is 0. B dot dl is 0 out here because the magnetic field is 0 out there. B dot dl is 0 over here because it's perpendicular, and so the only, what we have is B times L. And that's equal to the 4 pi over C times the enclosed current. And what's the enclosed current? N times L, because we have N turns per unit length times L, so that means N, middle N times L is the total number of length. Is that positive or negative relative to how I drew?
You don't have the current in there.
Sorry?
There's no current term.
Times I, yes. Is this positive or negative?
Positive?
Positive, right? Because we drew the loop this way and the flux is into the board, so it's all, that's a positive integral, so that's good, that's consistent. And so what we get is for a solenoid, the magnetic field inside, so V is 0 outside, and inside, it's 4 pi Ni over C, or 4 pi over C times the surface current flowing around the, and that is consistent with the boundary conditions that you're familiar with and that you're reviewing in your homework, that if you have surface current density, there is a discontinuity in the tangential component of the magnetic field across that surface. Since we have surface current density here, the magnetic field that is tangential to the surface, in this case in the z direction, jumps from 4 pi over ck to nothing, which is consistent with the boundary condition. Okay? And, you know, there are other examples. The other example, we'll just skip it, is thinking about a plane with current flowing on the plane, in which case we'll have magnetic field above and magnetic field below. Then you can do a quick little Amperian loop to show that the magnetic field above is 2 pi over ck in magnitude, and this guy is minus. If I call this the x direction, this is the minus x direction. Again, a discontinuity of 4 pi over ck as I go through that surface. All right? Okay. All right, so trivial stuff, just a quick review there. So what we want to now look at, we're going to think about more about the more general solution field equation. Thank you. Again, our field equations, B, del dot B is 0, which implies that B is equal to the curl of a vector potential. And the curl of B is equal to 4 pi over C times J. So if we plug now the equation for the magnetic field in terms of the vector potential, this implies that this is equal to the curl of A, plugging in for B. And the curl of A is everyone's favorite identity, the gradient of the divergence of A minus the Laplace of A. Okay? So this is the general PDE that relates the source to the vector potential. And if once we have the vector potential, we can find the magnetic field by taking the curl. It's a little yickier than we had in electrostatics, where we just had Poisson's equation, gave us the potential, and then we took the gradient to get E. Okay, however, you remember we have this business of gauge invariance. That is to say, and I always forget this, I don't even know what the word gauge actually means in this context. If anyone can really help me remember that, every time I teach this course, I look it up and then I forget. But I don't know what the word gauge means here, why it's called gauge.
Like railroad tracks.
Maybe. Maybe, 19th century London is where all this stuff is done, or a good part of it. All right, what's gauge invariance? Well, what we see here is that the physical force on the charges depends on B, not A. A is something that is a convenience, but it's not, there's no force that depends on A. We had one very simple, in the context of electrostatics, we had, one sort of degree of freedom that was arbitrary, which was the place at ground, where we put ground. It was arbitrary because the physical forces only depended on the gradient of the potential, not the absolute value. We have a more general kind of flexibility here in that the A itself is a vector field. A itself depends on the curl of something else and the gradient of something else, right? Because we said from the Helmholtz theorem, all vector fields that can be expressed in terms of the curl of something else and the gradient of a scalar. However, the B only depends on the curl of A. So what that says is that if I take A and I transform it by adding to it the gradient of a scalar, which is called the gauge potential, well then B doesn't change. Why? Because the curl of the gradient is 0. So, what that says is that we have a freedom, which is called the gauge. This transformation is known as a gauge transformation, and the fact that the forces are independent of that gauge transformation is to say that the equations are gauge invariant. So we have, in the same way that we could choose ground wherever we wanted, we can choose whatever gauge we want. And especially when we talk about electrodynamics and we talk about radiation, there are different choices of gauge that we use all the time. We kind of go back and forth depending on what's convenient. In the context of magnetostatics, there's a kind of natural gauge that we almost always choose. You don't have to, but it's just sort of the natural thing because it makes the equations just look nicer. And in particular, in magnetostatics, we fix the gauge by choosing what the divergence of A is. You see, what the curl of A has to be is fixed by, it has to be equal to B. But the divergence of A is completely arbitrary, and we can shift it around by different choices of gauge. So fixing the gauge is another way of saying, what the heck are you going to make the divergence of A? Make it something. And what we choose is del dot A is 0. And if it's not, we can always shift it by a gauge transformation to be 0. There is some gauge potential which will do that. So fixing the gauge means fixing the divergence of A. Because the curl of A is the only thing that matters. The divergence of A is arbitrary. Make it whatever you like. Okay? So making the divergence of A is 0 is convenient because then we have a very simple equation for, or simple-ish, simpler equation for the vector potential. Okay. So what this equation is, this is the gauge in with del dot A being 0. And in fact, remember last lecture we had this equation. I mean, the Biot-Savart law kind of had that buried in there. This equation is such that I have three equations. An equation for the x component, an equation for the y component, and an equation for the z component. But they're not independent equations because we must have this be true because we fixed the gauge. So generally speaking, even each one of these looks like a separate Poisson equation, a Poisson type equation for the x component, y component, and z component. If my currents aren't flowing along the x, y, and z direction, this is a giant mess. And in general, it's extremely hard to solve this equation. It's nowhere near as simple. All the tools of solving Laplace equations with Green's functions and boundary conditions are just much more complicated in the context of magnetostatics. And it's rarely done, at least to my knowledge. There are tricks of the trade where you can look in certain regimes where the magnetic, you have a sort of a pseudo-potential with pseudo-magnetic charges that make the magnetic fields look like electrostatic fields away from the sources. Because of course away from the sources, del cross B is 0. And away from the sources then there is a pseudo-potential, which is the gradient. If the curl is 0, then it's equal to the gradient of the scalar. But, you know, there's all kinds of tricks of the trade there. If we really wanted to delve into the guts of magnetostatics, we'd get into that. But just we want to get the big picture overview here so we can get to the good stuff. All right. So given this fact, oh, of course, we do know the formal solution to this equation because we know the Green's function for Poisson's equation. So the formal solution to this is A as a function of x is equal to 1 over c, integral with respect to the sources times the Green's function. Bless you. Again, J is a vector here, which makes this more complicated. Even for the simple problem that we have in the homework, we have to be careful, even though we might have constant in magnitude surface current density, the direction of the surface current is varying as a function of position, in which case you have to take pay very careful attention to how the direction is changing as a function of x prime. In your homework, you got to pay careful attention to that. Because we have, for example, in the sphere that's rotating, the current density is in the phi hat direction. But the phi hat vector is a function of where I am on the sphere. It's not a constant vector. And so you have to put that in somehow to do that integral. Think about that one. All right. So, given that generally the exact solutions are hard, we need approximation methods. In particular, we're going to look at the issue of the multipole expansion. In magnetostatics. So the problem, as we had in electrostatics, is that we have a localized current distribution. And we want to find the magnetic field. And to start, we find the vector potential at some point of observation where the distance from the origin to the point of observation is much, much bigger than the distance from the origin to any of the sources. So in the multipole expansion, we're looking at this condition. Okay, so as we did in the electrostatic case, we can do this in general by Taylor expanding the Green's function under this condition. So we use the same Taylor expansion that we derived in the context of electrostatics to write the Green's function as a sum over polynomials. That's the Taylor expansion about x prime equals 0. Okay? And thus we have the general form of the vector potential as a sum of multipole contributions, where AL is equal to, I'll put it up here. Minus 1 the L over L factorial integral over the source j at x prime to the L. Okay? So, the first term would be the monopole. L is 0. So this is equal to that. Okay? Now, if for example, we had a loop of current in magnetostatics, then we know that we could rewrite this as, in that particular example, j d cubed x becomes I dx, right? And in that case, and I, it's a magnetostatic case, I is constant. It would look like that for a loop of current. Of course, if I add up the dl vectors, if I have this loop, I'm not dotting this into anything. It's not like the b dot dl, where that dot product was the same. This is this dl vector plus that dl vector plus that dl vector plus that dl vector, blah, 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 comes back, the head eats the tail, and this is 0. Right? If you add up all those dl's, they'll add up to 0 around the loop. So, of course, the monopole is 0. In fact, it doesn't matter that I had a loop of current in this case. If I have a bulk density, there's no way I can get this integral, since the current is localized. The integral of this localized current must ultimately, if it's a steady current, the head must eat the tail. And you can see that formally in a kind of nasty way. Suppose, for a reason that seemed completely nuts, I consider the divergence of the ith component of x prime multiplied by the field j x prime. I don't know. Let's consider that. This is equal to sum over j okay. The divergence with that. So this is sum. So now I can multiply this through the partial, I should do the partial prime, sorry. The partial of x prime respect to this is delta I j times the current density plus x prime times del dot j. Right? Because once I get that through, this is del dot j. But what's del dot j?
It's the negative of 0.
D rho dt. In this case, we're talking about magnetostatics, so this is 0. Del dot j is 0 in magnetostatics. Sum over j is ji. So, what we see here in this completely unmotivated but true identity, the integral over all space of the current density, which is the thing that comes into the magnetic monopole is equal to the integral over all space of the divergence of the tensor x prime. And by the Gauss law, this is the surface integral at infinity of okay. However, we have a localized current, so there is no current flowing out to infinity. So this is 0. So, no magnetic monopole. What about the dipolar term? So the dipole term, A1, is equal to, let's put in L equals 1 into that expression. We have minus 1 integral v cubed x prime dot into grad, j x prime dotted into grad 1 over r. That's the L equals 1 term in that expression. Okay? So, boy, magnetic fields are fun. So, got some tensor junk to do. So let's see, what the hell does this mean? So this is minus, let's look at the ith component of the dipolar field, or dipolar vector potential. So that's the ith component of J. And then we have this dot product, so new dummy variable. Okay, and this is integral over x prime. Now, we note here that this is, remember, when we looked at these gradients of 1 over r, they were related to irreducible tensors. And since we're only looking at the vector term here, we only have the vector term of this irreducible tensor. And that vector term was related to the anisymmetric part of this tensor. That's the only term that survives when we do this contraction. So we keep only the antisymmetric part. And so that's Ji xj minus j sub j, jj, x prime to I over 2, partial j, 1 over r. And this anisymmetric tensor, we know, has 3 independent components, which are the 3 independent components of the cross product between those two guys. So that is equal to minus the integral over x prime with the half out front, epsilon ijk j at x prime crossed into x prime k partial j 1 over r. And that's equal to A sub I. So, final trick here well, not trick, but we notice that we have epsilon ijk of this vector and that vector, but in the opposite order. So if I switch the k and the j, and I really hate it when I do that, but that's what's going to happen. I can switch this order because I put a minus sign there. And so we come up with the final expression for the magnetic dipole contribution to the vector potential. It's equal to the cross product between a vector I'll call M and the grad of 1 over R, where M is equal to, or this is minus that, it's minus sign. M is equal to half the integral over all space x prime cross into j. Oh, rats. I forgot my 1 over c everywhere. Stick it in. All the j's have to have 1 over c's. All right? Yeah.
Does this have like the same property as the electric multipole moments of being independent of your?
It does.
Okay.
So the lowest non-vanishing multipole is independent of origin.
Okay.
Okay, and this is the magnetic dipole moment. So it's messier. Everything's got a cross product in it in magnetic fields. If you could put a cross product in, you probably should be there. So let me just quickly remind you. In electrostatics, we had the dipolar potential was equal to P dot R hat over R. Sorry, R squared. And the dipole moment was the integral over the source of x cross, no cross, times rho, right? And the electric field associated with an electric dipole minus the gradient of phi is equal to 3 r hat dot p minus p over r cubed. Okay, magnetostatics. The vector potential has a different form. Of course, the gradient of 1 over r is r hat over r squared. So this is m cross into r hat over r squared. The minus sign gets rid of that, minus the grade. That's so it has the analogous form, but one's got a cross product and one's got a dot product. The magnetic dipole moment looks kind of like the electric dipole moment, but it's got a cross product, and because that's got that 1/2 cross into J over C. Kind of looks like this, but not exactly. And the magnetic field, in this case, well, this is the curl of A. Let me write this out as minus the curl of M cross the grad of 1/r. Now, to save some time, you can look in the notes. It's a good exercise for you to do out all that tensor algebra. And you will find that this is equal to minus the grad of M dot R hat. So, the moral of the story is, boys and girls, the magnetic field associated with the magnetic dipole moment is exactly the same as the electric field associated with the electric dipole moment. If I know they are, therefore, they're dipolar fields. They can express in different ways in terms of vector potentials and scalar potential, but the fields are the same. The magnetic field of magnetic dipole moment is the same as the magnetic field, as the electric field of an electric dipole moment. And what does that field look like? Well, so if I have a physical electric dipole, that constitutes two charges, plus and minus. It's not a pure dipole field, but it's dominantly dipole far away from the charges, right? I mean, it's got also this thing's got an octopole moment, but that becomes tiny once I get far enough away, and the dipole dominates. And we know what the field looks like. Plus the negative. Whee! 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 All right, I won't say it.
It's a happy day.
Right? So, that's my physical electric dipole. The physical magnetic dipole is a current loop, for example, which looks like this. Of course, these fields are dramatically different near the source. For example, this field never has a divergence because del dot B is always 0. So all the field lines never originate or terminate anywhere. They must always these closed field lines, whereas the electric fields emerge and converge on point charges. If there were magnetic monopoles, well, we would converge and diverge from magnetic monopoles. But far away from this, the fields are the same. They're both dominantly dipole fields, and they have exactly the same form. Is that clear? All right. Okay, so calculating the magnetic dipole moment. So it's generally an annoying thing to do, but you know, I'm an annoying guy. So now there's one case where it's a little less annoying, and that's the case of the magnetic dipole moment of a planar loop of current. So if I have current flowing in a loop in the plane, here it is, I want to know what is the magnetic dipole moment associated with this current distribution. Well, I got to integrate over the source. There's my expression somewhere or other. There it is. 1 over 2c. Instead of integrating over the j d cubed x, I integrate I dl. Okay, and then I have to cross that into, so I is constant, it comes out. So if it's a steady current, it comes out. So I have dl, right, x prime crossed into, that's x prime cross IDL. Yeah. All right. So now we look at this and say, all right, here's my little DL. Here I am. Here's my position on the source. And I note that since this is the tangent to it, that this is equal to base times height of this triangle. And 1/2 base times height is called the area, boys and girls, of the triangle. So this is equal to I over c integral dA, which is I times the area of that loop over c. And of course, the cross product is in the n-hat direction, normal to the surface of the loop. So, the magnetic dipole moment, the only formula anyone ever remembers, the magnetic dipole moment of a current loop is the current times the area over c. All right, in the direction. So, that's for a loop of current. Now, we can use that as you're doing your homework if you can break up the true current distribution that's not constrained to a wire into an integral over a bunch of loops. So for example, let's suppose I have a rotating disk of surface charge. So I got a disk. It's rotating about its axis at a constant angular velocity omega. The disk has some radius r, upon which spray the sigma on there uniformly. And I want to know, what is the magnetic dipole moment associated with this current, surface current, which is flowing around here? So there is surface current density, which is flowing around here, depending on the local velocity. And of course, the velocity is just omega cross r. Okay? And r being this vector, so this is omega r in the phi hat direction. Okay? So that's my surface current, and I want to know what is the magnetic dipole moment associated with this current distribution. Well, the way to do it is to break this up. Let's just look on the top view. Into, stand in front of the damn thing, George. All right. Into differential rings. And each ring has within it a current VI. And so the differential magnetic dipole moment associated with that differential ring is VI times the area of that ring, pi r squared, over c. All right? So what is VI? Well, it's the current, the charge per unit time flowing around that circle. And that's equal to, we have surface current density flowing through that little dr. So remember, K is the current per unit length, and it's fluxing through that little dr. So di is K at that r dr. And that is equal to sigma r dr. So that tells me that the total magnetic dipole moment, the magnitude of it, is the integral from 0 to r of the m as a function of r, which is equal to, put all this together, pi sigma omega over c integral r cubed dr from 0 to r. That is equal to pi sigma omega over 4c r to the 4th. Does it have the right units? Well, it's got to be current times an area over C. All right? So, does the top thing have the unit? We got the 1 over C, so that's fine. Does it have the units of current times area? Yeah, because sigma is charge per unit area. So that gets me 2 of the r squares. That's charge per unit time r squared. Yeah. Of course, it also has units of charge times distance, which it has to because dipole moments are charge times distance, whether it's electric or magnetic in the right unit. So then we could check. You know, you got to check. Is it really R to the fourth? What the hell does R to the fourth mean? Well, you got to check. The only way to check is that it's got the right units. At least it's got to have that. All right. So,
Dr. Deutsch,
yes, sir.
how do you get direction out other than just like throwing in an hat at the end? Because K has a phi hat direction.
Right, but the direction of the magnetic moment is not the direction of the current.
Yeah.
It's the direction of the normal.
So it's
to the
just
loop.
automatic. It's just always the normal. You just throw
It is,
Okay.
because that's what this is the definition. X prime cross DL is in the normal direction. Of course, it's for a planar loop that it's in the normal direction. If I have something that's not a planar loop, I've got to add up the normals to each planar loop. If I broke it up in a funny way, I'd have to add up the directions. Here, each one of these loops has the same normal, so it's in that direction.
So just throw it on.
You just throw it on.
All right.
Yes, sir.
Well, couldn't you also look and say, well, your X direction is this way and your phi hat is this way, so correlates?
Yeah, I mean, at the end of the day, this is the formula, so it's not really ad hoc. It's just, once we've done it, once we're loop, we don't have to think about it. It's always just normal to the loop according to the right-hand rule. But if we have many loops, we've got to add up all those normals. Okay, it's the new normal. That means we're pretty early. Got to get over to Cotown. All right, have a good afternoon, everybody.